So now we can repeat this process for what we did with the Blasius moment or Blasius force. We can now repeat for the Blasius moment. So what I have here is the general equation W of z in terms of the net flow and the circulation, and then of course this is the Laurent series expansion. So this is a general form of the complex velocity, and then we have this equation from Blasius. This is a Blasius relation for the pitching moment about the origin as a function of that Wz, as a function of that complex velocity. So again, for the pitching moment, what we need is actually Wz squared. We need that times z. So we saw in the previous lecture that Wz squared can be written in terms of an infinite series in with bn coefficients, and Wz squared, if you just take this equation and square it, these are the coefficients that you get out here for these bn terms. We showed the first the first three coefficients here, and then of course you could keep going. So so we're going to take the exact same approach, and again this integral we're going to integrate in a perfect circle that is large enough to encompass the domain of interest. We're going to integrate from 0 to 2 pi around that circle, and again replace z with r e to the I theta, and dz equals I r e to the I theta d theta. So we can integrate in theta from 0 to 2 pi, and again, a bunch of terms drop out, and it turns out that this moment, once we integrate that around the circle and include all these terms from this Laurent series or from this infinite series here, once we include all those, turns out that the moment only depends on B2. So it's equal to pi rho times the real part of I times B2. Okay, well, it just so happens that we know what B2 is. We've found that here, and so we can plug that in, and what we get is pi rho times the real part of I times lambda plus I gamma over 4 pi squared. And this term is also squared, plus 2v infinity e to the minus I alpha times A2. So it will depend on the second term in the original Laurent series. Okay, so that's our equation there, and actually we can simplify this down further, and say that m, the pitching moment, is equal to 2 pi rho v infinity times the real part of I e to the minus I alpha times A2. Okay, so this is our final equation here. This just simply gives us the pitching moment as a function of, the pitching moment on any two-dimensional object. It wouldn't matter what that object is, as long as we know A2, or the second term in this series. Actually, it's the first term that we haven't shown here, and of course you'd have to solve for that somehow. You'd have to know what that is. We know what it is on flow over a cylinder, but for other geometries, we'd have to figure out what that A2 term is. And I should say that the reason we were able to simplify this down to this is that for incompressible flow without blowing or suction, lambda equals 0, and actually I gamma squared is equal to minus gamma squared. So anyway, when you plug those things in, that's why we can simplify it down to this equation here.